So far we've discussed charge pumps and how to generate non-overlapping clocks, given an initial clock signal. Now I'd like to discuss various ways to generate clocks, and that's generally going to involve some type of oscillator. Now, there are many, many ways of building oscillators, and I'm going to show a handful of them here. In fact, sometimes you can build one by accident when you're not trying to make an oscillator. And I know nothing about this. Don't even ask. So some circuits require very precise timing, and those circuits, like the PWM circuits, they're going to need a trimmed clock. You need very precise timing. But there are other circuits, they just need a clock that might be fairly loosey-goosey, not a whole lot of requirements for the frequency or duty cycle. So I'm going to show a couple different oscillators. Some might give you the precise timing needed for the PWM circuits, and other ones are just there to generate a clock if you need it. So the first oscillator I want to show is a ring oscillator, and we've probably all seen these before. So if the enable pin is driven low, the NAND gate is forced high, the output of the NAND gate, and this circuit is going to just sit in the logic state shown here. However, if you pull the enable pin high, the NAND gate now starts acting like an inverter. Therefore, we have 4 inverters and a NAND gate acting like an inverter hooked up in a loop, where the output of each inverter is connected to the input of the next inverter. So this is basically 5 inverters hooked up in a loop. Since the number of inverters is an odd number, there's no stable DC state that's going to satisfy this loop. For example, let's arbitrarily assign a value to the output node of the NAND gate. We're going to call it a high. Now we're going to follow that state through. So next one will go low, next one will go high, next one will go low, next one will go high. That gets fed back around, and it changes this to a low, changes that to a high, changes that to a low, changes that to a high, changes that to a low, and that gets fed back around. You can see this thing is just going to zing and oscillate, ones and zeros all day long. So the period of oscillation is basically going to be twice the propagation delay around this loop. Very, very common oscillator, ring oscillator. You just need an odd number of inverters to make this work. Now, you can adjust the oscillation frequency by adding or subtracting more inverters, or you could say, oh, I'm going to add some RC time constants in here, to make the delay a little bit longer from one inverter to the next. However, there's still going to be a different range of frequencies just due to process variation. And if that distribution is unacceptable for your application, there is a possible way to trim a ring oscillator using currents, and I'm going to show how that works. So the frequency of the oscillation can be adjusted by limiting the available current as shown here. So normally, all these gates, the NAND gate and the inverter, they go right to the positive supply. But instead, if you insert a current source here, and then if we can trim that current source, that limits how much current each of these amp or gates can pull or use to drive their output node. So by lowering the available current, you can lower the frequency of oscillation, or you can raise the current and increase the frequency of oscillation. So you can use this technique to minimize variation in frequency by setting the supply current low enough such that the supply current is the dominant term in the frequency loop here, not necessarily the propagation delay through the individual inverters. You're kind of limiting it by the current. Then if you make this current a trimmed current and you make it a stable over temperature current, then we call that an ITAP current. It's sensitive to absolute temperature. You can get a pretty decent frequency, trimmed frequency over temperature using this technique. So just to let you know, there's a possible way of trimming a ring oscillator. Okay, so the next oscillator I want to talk about, I'm not sure I know the real name of this thing. This is kind of the loosey-goosey oscillator if you just need a clock. And I'm just calling this the RC oscillator. Here's what the circuit looks like. It has an enable pin similar to the ring oscillator we showed earlier. When the enable pin is pulled low, this thing just sits in the state shown here. However, when you pull this high, now this circuit is going to start to oscillate. And this resistor R1 here provides some positive feedback because it connects the output of the NAND gate basically to its input. And when you pull the enable pin high, that NAND gate turns into an inverter. So you have an inverter with its output tied to its input, and the inverter doesn't like that. It's going to want to, oscillate, or you get some positive feedback there. In some ways, this looks a lot like the ring oscillator, just without all those extra inverters in the feedback loop. However, the RC time constant here makes a difference. Prior to the enable pin going high, node V3, which we're showing right here, is in the high state. Therefore, when the enable pin goes high, V1 is going to go low, and V2 is going to go high immediately. The low to high transition on V2 is going to couple through capacitor C1, and it's going to try to pull V3 up. If you take the right side of capacitor C1 up, the left side wants to follow it. So it tries to pull this up. So initially, it's going to pull node V3 a little higher than VDD. But as time goes on, V3 is going to be pulled down by the resistor R1 because V1 is now low. So eventually V3 gets pulled back down again. When V3 gets pulled down low enough, NAND gate switches, and that causes V1 to go high and V2 to go low. So this high to low transition couples through the capacitor again, and that pulls V3 even lower. However, over time, V3 is going to get pulled up through this resistor R1, and then it's going to flip the NAND gate again. So this cycle starts all over again. So this oscillation is pretty much controlled by the RC time constant here. Again, I wouldn't recommend using this oscillator in any kind of precision application, but if you just need a quick and dirty clock, this works pretty well. Okay, so the next oscillator I want to talk about is, I call it the Sawtooth Oscillator, and some of the PWM guys may be familiar with this. So this oscillator uses a fixed DC current, that's its I1 current, to charge a capacitor C2. And so what you get when you have a fixed DC current charging a capacitor is you get a ramp. And so if the current is a DC current, you get a nice ramping voltage. So the way this works is you have a comparator and you have a reference voltage on one side of the comparator. And let's say this ramp starts out at some low value, something lower than Vref. As the ramp rises and it reaches the Vref point, the comparator flips. And now we have that comparator changing state, triggering a one-shot. And this one-shot is going to have a delay associated with it. Or once it gets triggered, it's going to stay in a high, or its output is going to stay high for a little length of time here. And that's the width of this pulse. And the one-shot feeds back around and turns on a shorting switch. And that shorting switch is just going to short the cap out here. So the voltage on this node, it ramps due to the incoming current. But then when the comparator flips and the shorting switch gets engaged, it's pulled back down to zero. And it sits at zero until this one-shot basic timer runs out. And then it releases the shorting switch, and the cap C1 can start ramping up again. It ramps up again, it hits Vref, and the whole cycle starts over and over again. Kind of a nice circuit. You can trim it by trimming this current. You can also trim the capacitor. It's a very useful circuit, and the reason I call it Sawtooth is that's kind of what you get on the capacitor node here, C1. The comparator delay and the delay through the one-shot do come into the frequency component here. So it's not solely capacitor and current here, but you have to factor in all those, the current, the capacitor, and the delays through these other elements to get the frequency that you want. Okay, the last oscillator that I want to talk about today, I'm just going to call this an op-amp oscillator. Again, there are many, many ways of building oscillators. I like this one in particular. It looked kind of odd because it's an op-amp with both a positive feedback and a negative feedback. And you can kind of see on non-inverting input, we have a feedback going to a resistor divider here. And the R1 resistor is basically taking the output voltage, dividing it by 2, and putting it right on this node and feeding that into the non-inverting input of the op-amp. On the inverting input, which is the one you'd normally use for negative feedback, we have a resistor and a capacitor. So the way this works is, let's just assume the output starts in, oh, and by the way, this op-amp we're using is a dual rail op-amp. So maybe the supplies are plus 5 volts and minus 5 volts. So let's say the output starts at plus 5 volts. Well, what happens with this output at plus 5 volts, V out over 2 is going to be at 2.5 volts. And you're going to start charging C1 through resistor R2. So that's why you can see this waveform rising. This is going to rise up until it reaches the 2.5 volts. And then now the negative input has risen above the positive input, and V out flips, being all the way railed in one direction to, say, 5 volts, it rails all the way to minus 5 volts. And immediately V out over 2 goes to minus 2.5 volts. And now C1, which was sitting at 2.5 volts, starts getting pulled down through R2, and eventually it reaches the minus 2.5 volts on V2, and it flips the op-amp again. So this thing will just sit here flipping back and forth all day long between plus 5 and minus 5 volts. And again, I just thought this was an interesting op-amp to show because it has both positive and negative feedback, and you don't normally see that in an op-amp circuit.